Hey there, science fans! Have you ever wondered why water is a liquid at room temperature while carbon dioxide is a gas? Or why some substances dissolve in water while others don't? The answer lies in the fascinating world of molecular shapes and bond polarity. You see, molecules are like tiny buildings, and their shapes determine how they interact with each other. Just like the shape of a key determines which lock it can open, the shape of a molecule dictates its properties and how it behaves. Understanding molecular shapes and polarity is like having a secret decoder ring for the language of chemistry. So, put on your thinking caps and let's dive into the amazing world of molecular architecture. We'll learn how to predict the shapes of molecules, how to determine if they're polar or nonpolar, and why it all matters. Get ready for a wild ride through the exciting world of chemistry. Are you ready to unlock the secrets of molecules? Let's go! To understand molecular shapes, we need to start with the building blocks of matter, atoms. Atoms are made up of even smaller particles, including electrons, which are negatively charged particles that whiz around the atom's nucleus. Now, this all seems like I'm repeating information you already know, but it ties into molecular shapes, I promise. You see, electrons don't like to be too close to each other. They repel each other like magnets of the same pole. This mutual repulsion plays a crucial role in determining the shapes of molecules. When atoms come together to form molecules, they share electrons to create chemical bonds. This desire for maximum separation is what gives molecules their unique shapes. So, next time you think about a molecule, remember those tiny electrons working behind the scenes, dictating its shape. Pretty cool, huh? Let's talk about predicting the shapes of molecules. That's where the VSEPR theory comes in. VSEPR stands for valence shell electron pair repulsion theory. It means the shape of a molecule is determined by electron pairs around a central atom. Think of the central atom as a disco ball, and electron pairs as people on the dance floor. They spread out to avoid bumping into each other. VSEPR theory helps predict the most stable arrangement of electron pairs and the shape of the molecule. We can predict shapes like linear, bent, trigonal, planar, and tetrahedral. Remember VSEPR theory to understand the dance of electrons and the shapes they create. Molecules are three-dimensional objects, but we often represent them on paper in two dimensions. This can make it tricky to visualize their true shapes. But don't worry, there's a simple trick we can use: wedges and dashes. Imagine you're looking at a molecule head-on. Bonds that are coming out of the page towards you are drawn as wedges or triangles, like this. Bonds that are going behind the page away from you are drawn as dashes, like this. And bonds that are in the plane of the page are drawn as regular lines. Using wedges and dashes, we can create 3D representations of molecules on paper. It's like giving your drawings depth and dimension, allowing you to see the molecule in all its glory. So next time you're sketching out a molecule, don't forget your wedges and dashes. They're the key to unlocking the third dimension and seeing molecules in all their spatial splendor. The power of repulsion, lone pairs versus bonding pairs. Remember those electron pairs that like their space? Well, it turns out that not all electron pairs are created equal. Lone pairs, those not involved in bonding, exert a stronger repulsive force than bonding pairs. Think of it like this. Lone pairs are like those friends who need a little extra personal space. They tend to spread out more, taking up more room around the central atom. This extra repulsion from lone pairs can actually distort the shape of a molecule, squeezing bond angles slightly. For example, a molecule with two bonding pairs and two lone pairs around the central atom would have a bent shape, with a bond angle slightly less than 109.5 degrees, the ideal angle for tetrahedral geometry. So, when predicting molecular shapes, it's important to consider both the number of electron pairs and whether they're bonding or lone pairs. Those lone pairs pack a powerful repulsive punch. Understanding the difference in repulsion between lone pairs and bonding pairs is crucial for accurately predicting molecular shapes and understanding their properties. It's all about those electrons and their need for space. Molecular polarity, a tale of two poles. Now that we've got a handle on molecular shapes, let's talk about polarity. Polarity refers to the distribution of electrical charge within a molecule. Some molecules have an uneven distribution of charge, making them polar, while others have an even distribution, making them nonpolar. Think of it like a tug of war. If one team pulls harder, the rope shifts, representing a polar molecule. Electronegativity plays the role of the tug-of-war teams. It's a measure of an atom's ability to attract electrons. Different electronegativities create polar bonds. The shape and polar bonds determine a molecule's polarity. Understanding polarity helps predict molecular interactions. Methane, CH4. Let's put our newfound knowledge to the test and look at some examples. First up, we have methane, CH4, a simple molecule with one carbon atom bonded to 4 hydrogen atoms. Using VSEPR theory, we predict that methane has a tetrahedral shape with bond angles of 109.5 degrees. This is because the 4 bonding pairs around the central carbon atom spread out as far apart as possible to minimize repulsion. Now, let's consider polarity. Carbon and hydrogen have similar electronegativities, so the CH bonds are considered nonpolar. Even though the individual bonds are nonpolar, the molecule as a whole could still be polar if the bonds were arranged asymmetrically. However, in methane, the 4 CH bonds are arranged symmetrically around the central carbon atom. This means that any slight polarity in the bonds cancels out, resulting in a nonpolar molecule. So, there you have it. Methane is a nonpolar tetrahedral molecule thanks to its symmetrical arrangement of nonpolar bonds. Ammonia, NH3. But first, are you enjoying the video so far? Consider liking and subscribing so you can ace that chemistry class. Now that that's out of the way, let's get back to the video. Next up, we have ammonia, NH3, a molecule with 1 nitrogen atom bonded to 3 hydrogen atoms. VSEPR theory tells us that ammonia has a trigonal pyramidal shape with bond angles of about 107 degrees. This is because the nitrogen atom has 3 bonding pairs and 1 lone pair, and that lone pair exerts a stronger repulsive force, pushing the bonding pairs slightly closer together. Now let's consider polarity. Nitrogen is more electronegative than hydrogen, so the NH bonds are polar. Moreover, the lone pair on the nitrogen atom contributes to the molecule's polarity, creating an uneven distribution of charge. The overall shape of ammonia, with its lone pair pushing the hydrogen atoms down, results in an asymmetrical arrangement of polar bonds. This means that the polarities of the bonds don't cancel out, making ammonia a polar molecule. So, unlike methane, ammonia is a polar molecule due to its asymmetrical shape and the presence of polar NH bonds. Ammonia is a polar trigonal pyramidal molecule. Water, H2O. Finally, let's look at water, H2O, a molecule essential for life. Water has 1 oxygen atom bonded to 2 hydrogen atoms. Using VSEPR theory, we can predict that water has a bent shape with a bond angle of about 104.5 degrees. This bent shape is due to the 2 lone pairs on the oxygen atom, which exert a stronger repulsive force than the bonding pairs, pushing the hydrogen atoms closer together. Considering electronegativity, oxygen is more electronegative than hydrogen, making the OH bonds polar. Similar to ammonia, the lone pairs on the oxygen atom in water contribute to the molecule's overall polarity. The bent shape of water, combined with its polar OH bonds, results in an asymmetrical distribution of charge, making water a polar molecule. Water's bent shape and polar nature are responsible for many of its unique properties, such as its ability to dissolve many substances and its high boiling point. The significance of molecular shapes and polarity. We've explored molecular shapes and polarity, but why does it all matter? Well, these concepts are crucial for understanding the properties and behaviors of molecules. Molecular shape and polarity influence a wide range of phenomena, including solubility. Polar molecules tend to dissolve in polar solvents, while nonpolar molecules dissolve in nonpolar solvents. This is the principle behind the saying like dissolves like boiling and melting points. Polar molecules generally have higher boiling and melting points than nonpolar molecules of similar size due to stronger intermolecular forces. Chemical reactivity. The shape and polarity of molecules determine how they interact and react with other molecules, influencing the types of chemical reactions that can occur. Understanding molecular shapes and polarity allows us to predict and explain the properties of substances and their behavior in chemical reactions. It's like having a molecular toolkit that helps us understand the world around us. Conclusion: the building blocks of chemistry. Congratulations, science explorers! We've journeyed through the fascinating world of molecular shapes and bond polarity. We've learned how VSEPR theory helps us predict molecular shapes, how to visualize molecules in 3D using wedges and dashes, and how to determine molecular polarity based on bond polarity and molecular geometry. We've also seen how these concepts are essential for understanding the properties of substances and their behavior in chemical reactions. From the simple tetrahedral shape of methane to the bent shape of water, molecular shapes and polarity play a fundamental role in shaping the world around us. So, the next time you encounter a molecule, remember the dance of electrons, the power of repulsion, and the significance of shape and polarity. Keep exploring, keep questioning, and keep that scientific curiosity alive. Be sure to have a nice night, and good night. Like and subscribe for more content if you enjoyed.